What about the Gibbs free energy? If you have forgotten, you can always start from scratch. That tells you G is equal to U minus Ts plus PV. So G and if I do dg is going to be minus S dt. So du minus TdS plus PdV. I'll be left out with minus dt Sdt plus VdP, and this is going to be minus du n. So let's this is going to be plus mu dn. You can mentally do the differential here. The first term is going to be du, then minus TdS, and then if you took a differential of why is it dV here, it should be PV. Then this becomes plus PdV. But du plus PdV minus TdS is mu dn. That's the first law. And what are the differentials you're left out with? Minus S dt plus VdP. That is all you have over here. So this gives you three Maxwell's relation once again. Minus del S del P. Your T and N constant is del V del T, del V del T, P and N constant. Then you have del V del N, del V del N, P and T are held constant, and you see you have del mu del P, N and T are held constant. Finally it is minus del S del N, T and P are held constant. This is del mu del T, N and P are held constant. Now if you have followed the way we have derived all of this, then you can very easily check if these three Maxwell's relations are giving any new of these three, that you have a new Maxwell's relation. Look over here. Here, for example, in the numerator, the combination is del S, T and N. And here, so if you carefully look at this in the form of the Jacobian, the numerator becomes here. And in the right hand side, you are going to have del of V, P and N. So you're looking at a combination of a Maxwell's relation which will have del of STN and del of VPN. Have we derived that? Here. And again over here. So clearly, however way you write it down in the form of, whenever you write it down in the form of a Jacobian, this will not give you a new Maxwell relation. What about this? This is again V, P and T, this part, and the right hand side would be mu, N and T, this part, in the form of a Jacobian. Do I have V, P and T over here? So this one again does not give you a new Maxwell relation. What about this? This is S, T and P, and the left hand side is mu, N and P. Do I have STP combination? I probably don't have this, but one should still check. No. So I don't have this. So let's then del of N, T, comma P is equal to del of T, comma N, comma P. With the minus sign here, the minus sign I'm going to absorb in the denominator to give you del of ST, comma P, del of T and P is equal to del of mu and P and del of T and P. So you come up with a new Maxwell's relation, which is del of STP del of mu NP is equal to 1. This is a brand new Maxwell's relation which was not derived earlier. Look at H. H is U plus PV. So you do a differential in dH, which is du plus pdv. Now du plus pdv is TdS minus mu dN. So du plus pdv is TdS minus mu dN. So you have TdS minus mu dN. Is that correct? Or it's plus mu dN? Because your first law is dTs is equal to du plus pdv minus mu dN. Never forget your first law. And therefore this is, and then again you have plus of vdp. Once again you can write down the Maxwell's relations. It's a little bit of a laborious job, or rather boring and tedious job, but it's a good exercise that one should do at least once. So del T del N is equal to del mu del S. P is definitely held constant. Here S and P are held constant. Here N and P are held constant. Then del mu del P is equal to del V del N. Now del mu del P, entropy is definitely held constant on both sides. This is N comma S. This is P comma S. And finally you have del T del P is equal to del V del S. What are the quantities that are held constant? N is definitely held constant over here, and then S and N, and here P and N. Look at the combinations here now. In this you have del of T S P, and the right hand side is del of mu NP. I'm not writing the denominator, it should be obvious to you now, but you have this combination right over here. So this doesn't give you anything. Then you have del of mu NS is equal to del of V, P and S. So one has to go back and look whether we have this. I'm looking for a combination mu N and S. Do I have a mu N and S? So del of PVS, del of mu NS, and exactly what I have over here is PVS and mu NS. So this does not again give me any new Maxwell's relation. And finally here I have del of T S N, and the right hand side is del of V P N. This one I'm now already sure that we have it, and we can look up, and this is the one which was also derived from the internal energy U, TSN and PVN. So I have this combination here, so this 3. So therefore you do not get any new Maxwell's relations from this. You can very well write down, but they are not independent. They are the ones which we have derived already before. It's not a new Maxwell's relation that we have done. What else are we left with? We are left with omega. Omega, if I write down, is minus S dt minus P dV minus N d mu. So del S del V is equal to del P del T. Mu is definitely held constant. When you take the derivative with respect to t, v is held constant. Here your t and mu are held constant. Then you have del P del mu, del P del mu, V and T are held constant, del N del V, mu and T are held constant, and finally del S del mu, del S del mu, N and V are held constant, you have del N del T, mu and V are held constant. Now what I want to emphasize is that besides the whole idea of using Jacobians is to find out whether there are any independent Maxwell's relations. Jacobians in thermodynamics also has broad applications, we shall see later on, but Maxwell's relations also have the advantage that you can relate thermodynamic derivatives. For example, if you do not know what is del S del V, T and chemical potential is held constant, that is actually del P del T, volume and chemical potential is held constant. Now recall your equation of state, you had P as a function of equation of, you have for this particular system, you have equation of state, one is mu as a function of Tp, right, and pressure as a function of Tv, so one can eliminate the temperature or the volume. So let's write down this. So in hydrostatic system, I know that del S del V is equal to P by T, and del S del N is equal to minus mu by T. You can easily figure out the quantities which are held constants. So therefore this is one equation of state, this is another equation of state. So here of course P is a function, so you have three generalized forces, T, P and mu. Not all of them are independent, so you can write down P as a function of T comma mu, or T comma, yeah, so this is one of the relations. You can also write down mu as a function of T comma P. So these derivatives essentially are very useful in relating. So this might be a very complex derivative which is not straightforward accessible to you, but you can easily relate this. So this is one of the uses of Maxwell's relation. Anyway, coming back to the original discussion that we are having, that here if you see, then the first, let's look at this now. This one is St mu, and the right hand side is P, V and mu. Right. So do I have St mu and PV mu anywhere? I don't have. If I don't have, then I want to calculate this. This means St mu del of P, T and mu is equal to PV mu del of T, V, mu. So one can just interchange V and T here and T and S here to give you T S mu del of P, V, mu is equal to 1. So this is one Maxwell's relations which we did not have. What about this one? This one is del of PVT, this part, and del of N mu T. Do I have this combination somewhere? Let's check. Here. So nothing. This one cannot give me a new Maxwell's relation. Then again I have del of S and V. For this part I have del of S and V is equal to del of N mu V, not equal to. So on the right hand side I have del of N mu V. I'm not writing the denominator that I said earlier. S and V, let's see, do I have the S, and the combination would be S and V and N mu V. I'm sorry, this is S and V, this is N mu V, but that means my Maxwell, so if I work out the Maxwell's relation here, then this is mu N V is equal to del of T mu V. But this and this do not match. So one has to see whether we have written it down carefully. So del S, del mu T and V held constant is del N del T mu and V held constant. So this is the correct form. Therefore I have S of TV and I have N of mu V, and the bottom I have mu TV and T mu V. This is fine. So I have to look for a combination of STV and N mu V. Do I have a combination of STV anywhere? Look here. Therefore this is no longer known. So finally there are 6 independent Maxwell's relations, and we shall list them together. The first 3 follow from the Maxwell's relation, from the internal energy. 1, 2, and then I have 3. Then as we see, this is 4, this is 5, and finally this is 6. So if we collect everything together, del of TSN, del of PVN is equal to 1. You should always check whether you've written it down. Yes. Then the second one is PVS and mu NS. So del of PVS, del of mu N and S is equal to 1. The third one is TSV and N mu V. Del of TSV and del of N mu V is equal to 1. The fourth one is PVT and mu NT. Is 1. The fifth one is del of STP and mu NP is equal to 1, and the sixth one is del of TS mu and del of TS mu, del of PV mu is equal to 1. So these are the 6 independent Maxwell's relations that you have for a hydrostatic system. Right? We are going to end our lecture here and continue with it later on.